memorize, you know, like the parts and stuff. I know that's part of an anatomy class, but I can always go look that up in a book, right? You could. But do you want your emergency room person that's taking care of you in an emergency to say, wait a minute, I got to go Google that? Don't think so, right? Well, sometimes they have to, but not in an emergency situation, yes? Yeah, you can do it right there. Yeah, no. You don't want your brain surgeon to have to go Google that. Yep. You kind of want them to know that. Yeah. Exactly. Well, and to be able to recognize things that are wrong. Like somebody said to me today, and it's a nutrition thing, but somebody said to me, oh, you're only supposed to have 20 grams of fat a day. And I'm like, no, not 20 grams. Maybe if you're trying to stick to 20%, but that's not 20 grams. If you take a 2,000 calorie diet, 20 grams of fat would only mean that you're having 9% of your calories from fat. Do you know how many, what's your percentage? You should stick to 25 to 30%, or 20 to 30%, depends on the book you read. So 9%, that's way too low. So I didn't have the exact number in my head, but I knew that no, that's not right. I needed my calculator, of course, to figure out the number, but I knew it wasn't right because I understood the concept. Do you see what I mean? When somebody comes in with 100 milligrams of something that you know patients aren't supposed to get more than 10 milligrams of, you need to know that that's not right. See what I mean? So that's that. You know, you might know not exactly, and that comes with experience. But in order to get the experience, you have to have base. You have to have a base knowledge. You know, some of these little details, you're never going to remember them, and that's okay. But when you practice and use, you need to have the basic concepts down. So, all right, like, what's an exteroceptor? Yep, we ended up talking about that. So, from this chapter, we're going to define a few different nerves in the peripheral nervous system. When we hit the autonomic nervous system, we're going to just pick and choose a few things from that chapter. We're not going to make you, if you've looked at that outline and looked at the chapter, you're going, just calm, remain calm.
You want to tell us what pages to print on so we don't have to print 40-something pages again?
What is it? I don't think it's that long.
No, it's long.
It's long? Yeah.
It's like 18 pages.
Is it? I don't know which pages. I'm sorry. Maybe I could narrow it down for you, send you a little email or something. All right, so stimulus to the outside. Remember, when we're talking about sensory information, it's information coming where? Into the central nervous system from outside the central nervous system. Usually coming in what direction? No, coming from the out, going in. So give me a science name for that. Afferent, yes? The efferent is the opposite direction, coming from the central nervous system to the peripheral nervous system. What's another name for that kind of information? Efferent or motor. Yeah, see? She's learning something. Oh my goodness. So sensory, afferent, outside, in. Yes? We good? Who needs the sign-in sheet? You got to pass it back that direction. Oh, he's coming down. What a good boy. All right, so exteroceptors, information from the outside, pain, pressure, temperature, all that good stuff. Interoceptors, visceral organs, coming from where? Inside, that twinge in your stomach. Proprioceptors, balance, spatial stuff, where I am sitting up, laying down, walking up the stairs, walking down the stairs. Lots of different information has to be relayed depending on where I am in space. That's my proprioceptors. Again, think of the information coming in from things like tendons and joints and pressure on different joint capsules. General senses versus special senses. So the complexity of receptors can change depending on what we're talking about, what sensations we're talking about. When we have simple receptors, things that, and think of things that you want to happen quickly. Things like touch, pressure, stretch, vibration, temperature, pain, and where my muscles are, how much pressure I'm feeling there as well. Those are simple, and we tend to refer to these guys as general senses. The ones that we are a little bit more involved, we'll talk about second semester when we discuss information in chapter 15, are things like rods and cones, photoreceptors. Where do we find those? In your retina for vision, in your eyes. Hearing, where do we find that? Inner ear, and a little thing that kind of looks like a conch shell called the cochlea. Equilibrium, also in that same region, except we have little canals called semicircular canals. When we talk about smell, we have receptors on the surface of our nasal epithelium. And then when we talk about taste, we have receptors on our tongue. Those are all what we call the special senses, and they get their own special little chapter. If you look on page 486, table 13.1, we see some of these pictured for us. They're either encapsulated or non-encapsulated. Free dendritic endings, or they have some sort of capsule around them so that when pressure is applied to it, it then fires off those dendrites or starts the message going in the dendrite region. Usually think of things that need a little extra protection. We don't want to break off dendrites. So we see, encapsulated endings as well. So free nerve endings, typically find that in some connective tissue, find a bunch in the epithelial layers. And we're talking about what? What is skin? Excuse me. Skin, thank you. What organ is that? It's, no. Integumentary system consists of what? Well, excuse me. Goodness gracious, I'm allergic to you all. It consists of different cells. Stratified squamous epithelial cells with a basement membrane and connective tissue. Connective tissue underneath is called the dermis. So the organ itself consists of several different types of tissue, and we're going to find these receptors there. So think about your sense of touch. We can feel very tiny little touches, and where would those receptors tend to be? Think about your skin as a layer, like a sandwich. What would, if I'm just scratching the surface, very tiny, just barely touching, I can feel that, can't I? Where are those receptors located? Well, some of them are in the hair follicles, but they might be located closer to that upper surface in the epithelial layer. If I push down harder, I feel that too, right? Where might those receptors be? Down lower, in where? Yeah, in that dermal layer. So we see we have different types of receptors depending on what they are picking up for information. Non-encapsulated free nerve endings. We'll find it a lot in the epithelial layers, some in the connective tissue. Most are non-myelinated, small diameter. We call them group C fibers. They respond to things like temperature, pain. Some respond to pressure. Usually those are more deep, and they are going to be encapsulated. Thermoreceptors, what are they picking up? Temperature. And again, these tend to be simple. If and you'll do these experiments in lab, if I take an object like, we're going to do temperature discrimination, and we take these little things called mol probes. Typically you use them to dissect, but it's like a little metal probe. I'm going to stick it in water, hot water and cold water. I don't even have to touch that to my skin. I can bring it close to my skin and feel the difference in temperature, right? So those are the kind of receptors what we're talking about. Some of the lower heat receptors are more geared towards monitoring body temperature, and then those cooler temperature receptors are more towards the surface of your skin. Those are going to help monitor not only internal pressure, the deeper ones, but outside temperature. I think I just said pressure, I meant temperature. What's a nociceptor? Pain. So think about what pain involves. Typically some sort of damage, right? Some sort of chemical change due to damage. So if it's too hot or if it's too cold, we might actually feel pain. Also changes in pH, changes in chemicals. Who likes hot stuff? What is it that you like about those hot things? Or what causes you to sense those hot things? Not temperature hot, spicy hot. What is the chemical? Yeah, they're called capsaicins. And they actually measure the heat in Scoville units. Have you ever heard of that? So if you like it really hot, you have higher Scoville measures, but you're actually damaging receptors when you put all that hot stuff on your food. Same thing with onions. You actually damage receptors when you smell onions. People who tend to eat hotter foods do have a higher tolerance for those hotter foods, and I don't know, it might be because they're killing off receptors, yeah. Good question. No, that's the name of a product. I don't know if it has to do with the fact that it might have this chemical in it. I don't know. But yeah, there is an arthritis product with that name too. All right, so if I pinch you, or chemicals damage tissue, or chemicals like capsaicins are present, they can fire off nociceptors, pain. Light touch is associated with some receptors called Mercal discs. When we discuss the integumentary system, we're going to see this name again. So tactile, touch. There's also receptors in your hair follicles. If I tell you right now to rip out one of your hairs, you're going to wince. How come? It hurts. Why does it hurt? Because there's pain receptors there. Plus you're ripping out all the little epithelials that hold in hair. So again, on page 486, we see some of the different receptors. They're also listed in your notes. Okay, tendon organ, joint kinesthetic receptors, muscle spindles, all of these guys. So you should have a general understanding of what they do for a living. And those are encapsulated dendritic endings listed in your notes and in that diagram. So So, your perception of what's going on in your environment is going to help you survive in your environment. Your awareness of sensation is going to help you survive in your environment. You're a warm-blooded organism, so you have to maintain a core body temperature of what? 98.6 degrees Fahrenheit, 37 degrees Celsius, yes? So you have to react to your environment with sensations and then perceptions, interpretation of that stimuli. Don't go out today in your bikini because it's 10 below zero, yes? Somatosensory system is part of that whole sensory system that's going to help process information from things like limbs and body walls, in the walls of some of those cavities we studied in the first chapter. We're going to receive information from outside, balance, and interoceptors inside. There is some processing that's going to happen in the spinal cord, but most of your awareness of these sensations is going to be processed where? When I'm aware of something, where does the processing happen? Yeah, up in the cerebral cortex. So there's different levels of integration with respect to sensory. And we talked a little bit about this when we talked about the central nervous system and the fact that we sort of filter out some of our sensory information. If we didn't filter out some of this sensory information, we would be, exactly, we'd be on screech all the time. We'd be in sensory overload all the time. If you were aware of every single sensation you were feeling right now, that would be very stressful. So we have different levels. We have something called the receptor level, and that's the sensory receptor itself. Then we have the circuit level, where we're sending information, processing information, sending it to the central nervous system, or in particular to the cerebral cortex. And then once it's reached the cerebral cortex, for the most part, we have something called the perceptual level. And that's where we actually perceive and are aware of what's going on, or what the stimulus is giving us. On page 488, figure 13.2 shows us these different levels visually. So, when I want to produce a sensation, I have to get some sort of stimulus. Stimulus has to be received, and then depending on the intensity of that, graded potentials must reach threshold. What's AP? Action potentials. Okay, so I have to have enough of a stimulus to create enough message to reach the perception level. So I can have little stimulus, and sometimes I can filter out some of that stimulus. I could actually, when I pay attention to it, perceive it. Like when I say to you, your breathing rate. When I talk to you about breathing in and out, what's one of the things that you automatically do? You start breathing in deeper and breathing out deeper. You'll find this when you do your lab in the respiratory system, second semester. I'm going to tell you or talk to you about something called the tidal volume, the amount of air you breathe in and out. Now that's a non-perceptive thing until I point it out to you. Then what happens? You start exaggerating that. Yeah. Because you would distract them from thinking about what you're doing. Right? Because it'll be exaggerated if you mention it. That's what you're doing.
We debate why it's called action potential if it's happening in the moment. Why is it potential if it's pretense?
We could debate that.
But why though? What's your situation?
I have no idea. Yeah, because potential implies that it's not happening, but yeah, it has the potential to happen. Yeah. Good point. It's probably some physics thing that I have no idea about. Probably the physics guys would be able to help you with that one. But no, we could debate it, but we'd waste an awful lot of time, and I wouldn't have the answer to the question. So, nope. So, generator potentials follow this pathway. Some sort of stimulus generates potentials in the afferent. What's afferent neurons coming in, and action potentials have to occur. In those special sense organs, usually we have an intermediate guy, so we get some sort of stimulus. Then we have a graded potential, sort of a culmination of some of the stimulus that we're receiving are gathered and then sent on. So, for example, when we talk about the retina and how it works, we'll talk about cells called rods and cones that then hand off their message to another group of cells called bipolar cells. And then they hand off their message to another group of cells called ganglion cells. So when we talk about the special senses, we have a couple of other players in the pathway, and that's what this diagram or progression shows us. Neurotransmitters are involved in communication between neuron to neuron. When we talk about special senses, that stimulus can be very different. So it's not necessarily a chemical or a neurotransmitter. It might be light, or it might be sound waves, or it might be molecules dissolved in air to make you smell, or molecules dissolved in saliva to make you taste. So we have a little bit of a different pathway there. When I keep firing off sensory neurons, eventually, if they keep doing that, they're going to become damaged. So what they do is protect themselves. They protect themselves by sort of internalizing receptors for whatever the stimulus is. I'll give you an example. Anybody put on some perfume or cologne this morning? Spray, 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 smell, smell, smell. Do you smell it anymore? You still smell. Yes? Don't reapply. Okay? Just saying, less is good. Do not put too much. Why do you not smell it anymore?
Because you used to have
No.
sensory.
Yeah, this takes place.
Is that why, like, a lot of times you'll go into a store and you'll come up to an old lady or an older lady and it smells like she's taking a bath in it?
Correct.
Okay.
Yeah. Less is more. Especially you guys with the strong cologne. Really, honestly, less is more. So you stop smelling it because your receptors are protecting themselves. They go through a process called adaptation. They become what we call less responsive. And if, again, I like visual things, so I explain it this way. Think of the dendrites as having a whole bunch of receptors on them for that smell, whatever your perfume is that you put on in the morning or your cologne. When those molecules enter your nasal passages, they dissolve in the mucus and they fire off by attaching to those receptors and then opening them up and causing what to happen? This is the basis of a nerve impulse. We're in the dendrites. What happens? Say it again. Why?
Because there's blood in calcium. The gate opens up. I don't know what.
Yeah, but you got the wrong eye on. Sodium.
Oh, sodium. Yeah.
So the smell molecule attaches to the receptors, and we can see them all over the dendrites, those little purple things. And they open up the little floodgates. Sodium rushes in. Sodium comes in a wave. That wave reaches the... What area? Axon hillock. And it brings it up. Charge. It is the charge inside the cell. From minus 70 to minus 55. What is that called again? Threshold. And then that action potential fires off the neuron. So how do I slow that down? I still have the molecules in the air. And they're firing off, and they're firing off, and they're firing off, and they're like, holy crap, I am going to damage myself if I keep doing this. How do they do that? She says they desensitize themselves. What was it that caused them to fire off in the first place? If I take those receptors and kind of suck them inside and only leave a few out there, what's going to happen? Or it's going to take a lot more stimulus to do the same thing, because now I have a lot less receptors out there causing the flood to happen. So if you reapply, do you smell it again? Yeah. But what did you do? You took this many molecules and you put this many molecules into the... Now see, this is why you stink. Because you need this many molecules to smell it. Well, everybody else only needs that many. Yes? So don't reapply. So you have to intensify the stimulus once your receptors have undergone adaptation. And that's a protection mechanism for them. Like of course we're going to torture you in lab. I already gave you the heads up. I do enjoy the torture labs quite a bit. But when you stick your hand in something really hot, when you first stick it in there, it's like, holy crap, that's hot. And then after a while, it's okay. It's not so bad. Do you see why? Well, same thing with cold. So, receptor membranes become less responsive by sort of internalizing those receptors for whatever the stimulus is. Receptor potentials are then going to decline in frequency. So they're still kind of going to be there in the background, but they're going to be so low that I'm not going to what? Consciously be aware of them. They're going to be at a lower level, so I'm not really going to perceive them. You with me?
Yeah. I got a question. Is
Yes.
there an example of that? If somebody or an astronaut, obviously they train for this kind of stuff. They go to space with low gravity, distribute their cortex, it's awareness and balance. That's not going to be used if there's no gravity, right?
It's still going to, there's still going to be stimulus with respect to your position. So whether you're upside down or right side up. But you're not going to have as much stimulus from all of those muscle groups that send information about pressure.
Right, so their muscles become weak.
Exactly. And that's one of the big problems with weightlessness. One of the things that helps to stimulate bone formation, for example, is what? When I actively push down on the ground. So weightlessness, not as much pressure, is a problem with respect to bone growth and things like that.
I'm saying certain parts of the brain have become affected. So nothing in the brain is never not used.
Not affected in the sense of damaged, but as far as what it perceives will be different.
Say weakened, if they come back to Earth and all of a sudden there's gravity.
It's not the brain that's the issue, it's the what? Yeah, and the message that's being sent from those. Not necessarily the message to the central nervous system, but what happens when I don't send messages to my muscles. Yeah, exactly. You don't use it, you lose it. So you're not getting as much muscle stimulation. So that's what's more effective. Not necessarily pathways to the brain. Does that make sense? Okay, good. So, adaptation, different types. Fast adapting are called phasic receptors. And then tonic receptors adapt much more slowly. Our proprioceptors and our nociceptors. Too bad, because I wish the nociceptors would adapt phasically rather than tonically. You know what I'm saying? What's that mean? When you feel pain, you're going to feel it longer before you go into adaptation mode. You have both receptors in your stomach. Well, depends on what we're talking about stomach-wise. Sometimes, yeah, those stretch receptors. So they're more in the muscles that line the stomach. So pressure, it's a good thing there. Phasic and not tonic for all of you ladies who put your hair up in a ponytail. Yes? Because you feel it when you first put your hair up in a ponytail. Or if you just have long hair. What's happening? It's pulling on all those hair follicles. So those adapt quicker, which is good, because that would drive you crazy if you felt every single hair pulling on your head when you put your hair in a ponytail. That wouldn't work very well, would it? So understand the difference between phasic and tonic receptors, the adaptation difference. So processing at the circuit level, pathways. There's 3 different groups, and we've kind of heard this before, yes? We heard this when we were talking about processing in the spinal cord, right? First order, second order, third order neurons. And it's pretty self-explanatory. First order neurons are going to conduct impulses from the receptors, the outside guys, and bring them to where? Where does all the information go from here? It has to go to the central nervous system, right? So it's going to first go to the, which starts at, when I'm talking about these? Spinal cord, right? So the second order guys in the spinal cord are then going to pick up that information. So that it's kind of like the sensory interneuron, yes? That same pathway we talked about when we talked about a reflex arc. We talked about these guys and how they pass off information. Second order is going to transmit to the next group, third order, and that's going to conduct information what? Up to the brain. So we're going to conduct impulses through the spinal cord up. What's that called? Going up? Ascending. We're going to hit the thalamus, those central brain regions first, and then we're going to be sent to where we need to go depending on what that information is. So from the thalamus to the somatosensory cortex. That's my switch channel, which will send to different areas depending on what that stimulus is, whether it's smell, whether it's taste, whether it's touch. And it will send it to the place where it needs to be access files to be aware of, and that's my perceptual level. So first, second, and third order neurons are going to help me send that information where it needs to go. We talk a little bit about pain tolerance. Some of us have a higher threshold to pain, and it has a lot to do with what we perceive, the stimulus we send to our brains, and the perception of pain. So it's an actual chemical thing that allows somebody to endure more pain than others. Sometimes people get very frustrated with some people who have very low tolerance to pain, but it's a chemical thing, and it's a perceptual thing. Remember, what we perceive has a lot to do with the way we react to our environment. Why are you afraid of that spider? I hate spiders, by the way. I know that they're very good for the environment. They eat all kinds of nasty little bugs. They're just wonderful. But they scare the bejesus out of me. Yes? Even the littlest of stupid spiders will scare the bejesus out of me. And I know, I'm a scientist. There's not any reason to be afraid of the spider. But I am. Why? Something in my file cabinet that I can't seem to get rid of. Every time I see it, I access those files. It scares the bejesus out of me. I don't know. I always try to figure out, because, try to analyze why. Correct. That's where I was going next. So, don't scare the bejesus out of your kids. And I know it's hard to do that, because I can remember I digress for 1 second. I was taking my kids for a walk on the stream where we used to live, and they had drawn the stream way down, so there was tons of rocks exposed, which is really kind of neat because you can go and see if you can find fossils and things like that. So my son was turning over rocks, and he turned over this one rock, and there was a giant spider on it. It took every ounce of me not to scream like a psychotic woman when I saw the spider, but I'm thinking, no, you cannot make him afraid of spiders just because you're afraid of spiders. Unfortunately, he's afraid of spiders too. So it must have rubbed off somewhere. But yes, your perceptions can pass on to your children. Perceptions about many, many things. Yes, not only the fear of spiders, but other things, our belief systems. So that's part of our perception of our world as well. Yeah. Or if you see your mom smoking a cigarette, you're going to say, Mom does it. Yes? Or Dad does it. Yeah, that's perception, folks. You're giving that to those kids. Stop it. It's bad for them. Yes?
What about like child abuse? Like making them feel like they feel a certain way.
Exactly.
Like other things can trigger that.
Sure. Perception of your environment. Perception of yourself. Yes? Some people have a really good attitude about a lot of things in their life, their perception of situations. And some people, you can ask the same two people, and other people will be, horrible, terrible, the world is ending, right? So those are different circuits that we create. Those are our perceptual levels. Those are our files that we have. So the interpretation of sensory input depends on the specific location of those target neurons in that sensory cortex. Perceptual deduction, ability to detect stimulus sent to the summation areas of impulses. Magnitude estimation, intensity of things, and that's coded in frequency of impulses. So if I have more groups of impulses that are coming in for processing, the magnitude of something can increase. I think I've showed you examples of me picking up my bag. When all my computer crap is out of my bag and my giant heavy book is out of my bag, I can pick up my bag fairly easy. Yes? But what happens when all my crapola is in there?
It's not so easy.
It's the same movement, but the magnitude has to change. Yes? What do I have to do? I have to send much more message out to do the same thing. So that's what that is talking about. And spatial discrimination, identifying different sites and patterns, and you're going to do this in lab, discrimination of two different points. So again, different groups of neurons are going to send messages with respect to what you're feeling. And you're going to do this with a little device called calipers. So there's two little pointy things on this little thing that opens up and gets wider and wider. When you put the two together very, very close, and you touch our skin very lightly, it's very hard to tell that there's two things there. It's kind of like the resolution concept when we look through the microscope. As I move them further apart, at some point you're going to feel two separate things. Okay? Oh, why do we have to use spider as an example, all right? Jesus.
He wants you to start going like this.
Oh, there's a big spider on my biology lab book. I almost stopped buying it because I hate the big spider on the front.
So would the magnitude estimation be like somebody who's afraid of heights, but they climb on this chair and they have to like fix a bulb or something, and then they can just climb off of it, and it's kind of frightening to them, but not bad. So they go on a roller coaster and they just start freaking out, or is that
Not quite. That would be more of a perceptual deduction issue. Magnitude estimate, it's like intensity of things, whether it's very light versus not very light, or very loud versus not very loud. Same stimulus, but you're stimulating more. picking heavy things up versus light things up. Okay? Does that make sense? All right. And then, of course, spatial discrimination, extremely important in you going on that chair because you're afraid of heights. Well, spatial, when we think about spatial discrimination. So those are receptors that you're, or information that you're receiving about where you are in space. Some people intensify those or have a more aware perception of some of that stimulus versus somebody who doesn't. Sensory perception, abstract. What the heck is abstract? And that's what some of us have problems with. Anybody like word problems in math? Sonny goes down to the store and gets 7 apples and has 5 friends and, you know, that kind of stuff. So you identify more complex aspects and several stimulus properties. You're sending in information from a bunch of different things to get to a certain point. And that's what abstract is talking about. Quality discrimination, ability to identify submodals of sensations, like something is really sweet, or something is really sour, or something is sweet and sour. Pattern recognition, and a lot of this is extremely important when we talk about learning how to speak a language, or learning to read, yeah, or even doing math, exactly. So different patterns and pattern recognition are important. When I sit and listen to a certain pattern of music, I know what the song is based on what? Yeah, the pattern of the notes, what order they go in, how long they stay. Some people are better than that, better at that than others, right? We used to watch this show on TV. They'd give you a certain amount of notes, and then you'd have to figure out what the song was. And there was always that really smarty pants that could, you know, you'd give them 2 notes, and they'd say, "Oh, I know that song," and then somebody else would need 10 to recognize it. So pattern recognition is also extremely important. Again, this little guy sending information at the perceptual level, cerebral cortex. Those midbrain regions are going to channel that information to the motor cortex and the somatosensory cortex for processing. So perceiving pain, tissue damage, chemical changes, and some of the different fibers associated with a perception of pain are listed here as well. Some neurotransmitters like glutamate and a substance called P. That's nice because usually everything is very long in science, but we'll call it substance P. That works for me. Some pain impulses are blocked by inhibitory chemicals. So as a protection mechanism, sometimes some of those pain receptors are blocked by you when you secrete some of these substances. Endorphins, for example. Anybody like to run for long periods of time? Well, you like to run for long periods of time? There you reach a certain point where the pain, there's no pain.
It just goes away and you have this amazing body head buzz that like lasts through the whole day and it's stressful.
And why is that? Yes, you produce certain chemicals in the brain that help to block some of the pain and actually cause you to be euphoric. I have never reached that point. I can't understand why somebody would run 26 miles anywhere on purpose. Just saying. So those chemicals, some people enjoy that feeling, and that's a lot of people that do long distance running and things like that describe that you just did, that euphoric feeling from endorphins. So all perceive pain at same stimulus intensity, but our tolerance varies. Our sensitivity to pain Well, we all have the receptors that fire off, but some of us are more aware than others. Means low pain tolerance, not low pain threshold. So even though they are aware of it, they might still be able to take more pain. They're just more aware of it for a longer period of time. Your genetics helps to determine pain tolerance in response to different pain medications. Not all pain medications work for all patients. And some people can take a very small dose of pain medications and be, whoo, out cold. And others would have to take a lot to have the same feeling. I don't know. Redheads have a higher tolerance to pain?
Have a higher tolerance to pain medication and anesthesia. When I was getting my
Never heard that.
second cesarean stab in the back from two very inexperienced gentlemen.
Oh, there you go.
They were talking about that, and I thought that was interesting. And then last couple of months ago, my roommate, who's a redhead, fell down the stairs and was intoxicated. The stair broke on him though.
Yeah, but the intoxication part probably
But the
helped him with the,
intoxication- Well, they were back stairs, I guess, but
Yeah.
the intoxication put right in his balance.
yeah.
And he smashed into a metal, formerly sombrero-shaped ashtray that broke the bone and all. Saying, yeah, and he had to be admitted.
Oh, my goodness.
I went in and he woke right up and he was talking to me and while he's trying to talk to me.
Like I said, the alcohol probably had a little to do with that by the time he had that. Yeah, definitely people react, and you can see that if you've ever worked in hospitals or even taken pain medications yourself. We all have different levels of reacting to those pain medications. It has to do with basically the way we're wired in our genetics. So long-lasting intense pain, hyperalgesia, pain amplification, chronic pain. We also have something called phantom limb pain. Sometimes when something is gone, you have a limb removed or a finger removed or something removed where there were formerly pain receptors there. Sometimes you can swear you still feel it because you still have, think about the neurons, you still have, say, another half of an axon that leads up to a cell body somewhere. Eventually that's going to die out because there's no stimulus from the other end. But you can still, for a period of time, feel sensation from something that's no longer there. It depends on the person. It depends on their chemistry, body chemistry. And he's still sometimes. So you wonder if there's some, still portions of information or portions of neurons in nerve groups that are still intact. And just some sort of movement might fire them off enough for him to have sensation there. So it depends. It depends on the limb, depends on the person. So phantom pain, felt in a limb no longer present. Epidural anesthesia can help to reduce this. What's an epidural? Huh? Well, yeah, it's in your spinal column, and it's gonna affect typically what? Yeah, typically lower limbs or limbs.
Can nerves grow back together or reconnect?
Neurons, as long as their cell bodies are intact, can regenerate new fibers, and we'll talk about that here.
After my accident, with all the muscle damage and stuff, I lost sensation in a lot of the areas of my legs,
Uh-huh.
and now I'm getting it back.
Right. So yeah, they can, as long as their cell bodies are intact. Visceral organ stimulation, vague aching, burning, activated by tissue stretching, ischemia, chemicals. What's ischemia? Yeah, sometimes when tissue dies, necrosis. muscle spasms can also stimulate these receptors as well. And then we have something called referred pain, where we kind of fire off pathways that, how do I describe this? We fire off receptors in nearby pathways that don't necessarily reflect where the stimulus is coming from. Okay, give me an example of that. I'm having a heart attack. Yeah, the pain, the damage, the tissue damage is coming from the thoracic region, the mediastinum, the heart. But I get pain that kind of runs down my left arm and makes my fingers tingle, or in my face, in my jaw. That's what referred pain is all about. So your perception of the pain isn't really where the pain is coming from, because that damage is actually firing off some nearby pathways. So gallbladder attack will do the same thing. Because they're non-myelinated, not necessarily, but they're just in the same region. So they fire off receptors in similar regions that end up in similar pathways. If you work the holidays, I call them the eating holidays at the hospital. Thanksgiving, Easter, Christmas. Yes? You're very busy. Why are you very busy? Well, you tend to have a skeleton crew, but then you're going to be busy. I'm just giving you the heads up. Even though you get the time and a half, you're going to be on your toes. Because all those people that overate are going to come in and think they're having a heart attack. And they're not having a heart attack. You know what they're having? It's some sort of gastrointestinal disturbance. Sometimes a gallbladder attack. So many of your I think I'm having a heart attack patients, it's because you ate way too much turkey. Yes? And again, it's because of referred pain. So you will get that pain that you feel like you're having a heart attack. So it's best to go in, and the time and a half people need to get, make the money that they're making, so it's okay. Well, tension can cause pain to occur, vasoconstriction in the brain. So that's a little bit different. All right, so we see if there's any heart issues in this diagram on page, what page is that on? 490. We see some of the different places where you would feel pain associated with other places where that pain is being generated. So in the heart, down that left arm, in the jaw, in the uterus, you would feel more of a distributed pain, even though your uterus is way up further. In your urinary bladder, we're kind of in the same region. Kidneys. Anybody have kidney issues? Kidney infection? Where do you feel the pain? Yeah. Where was the pain? Yeah, way in the lower back. It can come all the way around to the sides and even down your legs.
When I first got my first kidney stone, I was 18 years old, and nobody knew what was wrong with me. I thought it was like GI or something, because, well, first I thought I ate something bad.
Yeah. But see where that whole, see where
But
the,
it was the whole region and my legs. Is that because the ureters goes, like, across like this kind of?
well, it might be the kidneys are up in your upper back, and then there's a pathway down to your bladder. So depending on where we're firing off pain receptors, it might be in that tool.
Yeah, that when it comes up over the hip bone, that's where the most painful spot is.
Yeah.
Because it's just the angle. And then when it goes from the bladder, it actually stays into the bladder.
Yeah. So that is a map of where I might be feeling pain and what might be causing that pain. Okay?
Do we need to know that first?
No. Just understand what referred pain is. All right. Structure of a nerve. On page 491, figure 13.4, we see what a nerve looks like. And what does a nerve look like? Huh? The bone? Well, it's more like muscle, actually. But there are little groups, like the osteons. Is that what you were thinking of? Yeah. They're called fascicles. So this is a group of neurons. So when I say nerve, I'm talking about a group of neurons. And these groups of neurons are bound together, just like wires in your house. And when I look at any given nerve, I might find sensory and motor neurons in it. Because each neuron, singularly, can only go in one direction. That's one of the biggest reasons why myelin is helpful. When I have a group of neurons, I want to make sure they're insulated so they don't fire off other neurons around them. So they're bundles of myelinated and unmyelinated neurons, peripheral axons enclosed by connective tissue. What's a peripheral axon? Axons that are outside the central nervous system, in the peripheral nervous system. So you should be able to identify these guys, and you'll probably see that diagram again. Where are you going to see it again? Yeah, on your next lab exam. Not this one coming, so don't be afraid. The next one. So we have something called an endoneurium. And an endoneurium, when I look at this, I think of a box of straws. You remember when you were in kindergarten? And then the teacher came around with the milk? Am I dating myself? Do they do that now in kindergarten anymore? They don't? You don't remember this? I remember it. The teacher would bring the milk, and then she'd have the box, the straws, the brown box. Oh my gosh, I remember the brown box. Oh, see, yeah, we all got milk, yeah. Oh, jeez. All right, okay, think of this. Teacher comes with a little box of milk, like in the old days. And they have the box of straws, the brown box. And inside the brown box of straws is a whole bunch of little white wrappered straws. Yes? Okay, so let's visualize the box of straws and think of this neuron. So the outside covering of my box of straws would be my what? Epineurium. Now inside the box there's a whole bunch of separate little straws. Those would be my... No, inside the box there's a single straw. That would be an axon. And it's wrapped. Well, the middle of the straw would be the axon. The straw itself would be the myelin sheath around the middle of the straw. And then that's got its own little wrapper around it. Each little straw, right? That's the endoneurium. Now, if the teacher wanted to grab a bunch of straws to give to a few people, she could grab a bunch of straws. Well, each group, some of the groups, are wrapped by their own little membrane called a perineurium. And each of those little bunches, they're not called osteons, they're called fascicles. Okay? I'm looking at the picture. So look at that picture on, oh, that's not good. Well, that's a real one. This picture here on page 491. So we have the epineurium around the whole box of straws. Then inside we have little groups of straws called fascicles. Those are wrapped up by perineurium. Inside those little groups we find little white wrappered straws. So the white wrapper is the what? Endoneurium. And when you open it up, you have a straw, the plastic part, and the thing that goes through the middle. The plastic part would be the myelin sheath, and the thing that goes through the middle would be the axons. Yes? There's your box of straws. When we study the muscles, we're going to see the exact same terms. They're arranged the exact same way, except we're not going to call them epineurium and perineurium and endoneurium. Guess what we're going to call them? Epimecium and perimecium and endomecium for muscle. So we're going to throw these terms back at you again, same exact terms, same exact places, but we're talking muscle. So that's what a nerve looks like. If you look at it up close and personal, you can actually see some sort of blood supply, which I forgot to mention. So in this case, blood vessel here. Now see all these little round things? Those are my straws on the outside, the straw wrappers, and then the axons run through the middle. What are these white things? Those are around bundles. What are they called? What are the bundles called? Fascicles. What's the membrane called? Perineurium. Okay? So you can see that here on the actual slide. So know those terms. So, classification of neurons. So that was under structure. When we talk about, not neurons, but nerves, we see that most nerves are mixed. So there's a combination of fibers coming in, fibers going out, or afferent, efferent message. Somatic and autonomic. What's that? Yeah, and somatic would be more voluntary, right? Okay, going to the body, or awareness, conscious awareness, voluntary, involuntary, we can use those terms too. But somatic and autonomic. So mixed nerves are both sensory and motor fibers, in and out. Impulses both to and from the central nervous system. And then there are a few that just have one or the other. Sensory or afferent nerves, impulses only towards the central nervous system, or motor efferent nerves with the information coming from the central nervous system. When you study the cranial nerves, which we're going to have to know those guys too, you'll see that some of them are mixed, some of them are sensory only. So pure sensory or afferent or motor or efferent nerves are rare, and most of them are mixed. So some of the different fibers we're going to find in a typical nerve. Somatic afferent, somatic efferent. You know what that means, right? Going to the body, coming in, going to the body, going out. Visceral organs. Coming in, going out. Peripheral nerves are classified as cranial or spinal. So anything that's out here that comes into the spinal cord first and then goes up. Why would I send information from here to the spinal cord and then back up again? Kind of be a waste of, yeah, well, it would be a waste of, it'd be like going around the block 7 times if I could just cut through somebody's backyard, right? So, cranial nerves, we talk about messages that are being sent typically from stuff up in the head. Groups of cell bodies that are associated with the peripheral nervous system. We've seen this term before when I described some of the different areas of the spinal cord. These groups of cell bodies called ganglia are associated with peripheral nerves too. And usually we see them just before nerves split to ventral or dorsal branches, just before the spinal cord. Dorsal root ganglia, sensory, somatic. What's ventral? Dorsal was coming in. What's ventral? Going out. So what do you think the ventral root ganglia is going to say? Is it going to be sensory? You think? No? What's it going to be? Motor. Ganglia associated with efferent nerve fibers contain autonomic motor neurons. Autonomic ganglia, motor viscera. And we'll see that a little bit in chapter 14. Mature neurons are amniotic. What's that mean? Excuse me, amniotic. They're also amniotic. Amniotic. No. When I put an A in front of something, it means no. Amniotic. No what? They don't undergo mitosis. If the cell body or soma stays intact, they do have the ability to correct fiber damage. So if we look on page 492, figure 13.5, we see the steps involved in the regeneration of nerve fibers. Holy moly, I can't talk today. So if axons get damaged or axons get severed, as long as we keep stimulating those nerves, they can actually regenerate and myelinate axon fibers. As long as the soma is intact, as long as the cell body is intact. So, axon fragments, or how do you say that word? Thank you. Can't talk today. Can spread from what's left down. So we can make axon further down, and that's what we see in this diagram. Macrophages are going to play a role in cleaning all the dead stuff out. We also have to regenerate the myelin sheath. So myelin sheath has to be regenerated as long as we still have some myelin up further before the damage took place. We regenerate the tube, axon regenerates, new myelin sheath forms, and that would make a nice essay question.
That actually helps me understand why my physical therapist kept telling me I had to rub those areas.
Yeah, or they might, when we have certain nerve damages, the physical therapy part of that might be to electrically stimulate different nerve groups. So they'll still stimulate those muscle groups so that they continue to receive stimulation and don't atrophy until you can regenerate those nerve endings and message.
I know when I came out of the coma, that this leg, they had it on a, it was an interesting thing. It made my leg move up behind it as it rotated.
Yep. And that's to keep those muscles from atrophying. Atrophy.
To prevent blood clots.
Yeah, that too. All right, so we can regenerate those nerve fibers. Bless you. And that's just more explanation on the same thing. We see the steps on that page 492 diagram. So again, that would make a lovely essay question. Now, 12 cranial nerves. Do you have to know them? Yes. Do you have to know them by name? Yes. Do you have to know them by number? Yes. So what is this up here? Oh, that's a mnemonic. Do you know what a mnemonic is? Well, it's a way to help memorize a list of something. You take the first letter from all of the things you have to memorize in that list and you create a little saying. So I always say, make up your own. Because, no, seriously. Because when you make up your own, when you take the time to make up your own, guess what's happening? Exactly. And it means more to you. Sometimes they can get a little dirty. That's okay. As long as you keep it to yourself. I happen to like this one right here. Once one takes the anatomy final, very good vacations are heavenly, very good. But those are the 12 cranial nerves. Lots of information in the book about the 12 cranial nerves. What do I want you to know? This. Yes? What's on your outline? Okay? So, olfactory, cranial, and I'll give you a hint on how to remember. How many noses do you have? One. That's your first cranial nerve. What is it? Olfactory. For your sense of? Smell. Receives what? Sensory information. If you look on that little chart right underneath this picture that you see, which is probably that, you can see that some of them are mixed, some of them are sensory only, some of them are motor only. I'm not too crazy about you having to memorize that, but just understand what it is, the name of it, its number, and what its function is. So sense of smell, olfactory, optic is your what? How many eyeballs do you have? Two. What's your second cranial nerve? Optic nerve. What's it for? Vision. Okay? So basically that's what I want you to know about the 12 cranial nerves. So olfactory is 1. And they give you a whole bunch of information. Optic is 2. Whole bunch of information. Again, just the name of it and what it does for a living. Oculomotor is 3. What does it do for a living? Yeah, it moves your eyes. By moving the what? Muscles that are attached to your eyeballs. Number 4, trochlear. What's that for? Directs my eyeballs. So I know you just said that. So what did I just do? I turned my head. That's a whole nother set of simulation. But then I also had to turn my what? I had to turn my eyes towards you too. So that's that stimulation of the eyes. Involved with information input from your what? Hearing, as far as where I need to place my eyes directionally. The trigeminal, number 5. What's that for? Yeah, so some of this, again, notice how we're kind of hanging out in the head region when we talk about all this stuff. So maxillary and mandibular helps to stimulate muscles that are going to help you chew up your food. Or, what else? You don't just chew your food with those muscles. I'm doing it up here right now. Yep, some talking. Or singing. Abducens, primary motor innervating lateral rectus muscle. What's that for? What are we doing with that guy? He's kind of confusing, but we're still in the eyeballs, believe it or not. Okay? So we're moving, side to side, eye motion. So we have up and down, we have side to side, and then we have directional. So there's a bunch of different guys involved in that. Facial nerve. What's that doing for me? Yeah, expression, muscles of expression in the face. But what else? When we look at the facial nerve, where are we on page? That's trigeminal. Oh, it's on page 496. Where's the? Oh, there it is. It starts on 497. So what else is hooked up to the whole facial nerve thing? Yeah, and we're going to talk about the facial nerve when we discuss sensory information that's coming from where? Your tongue. So it's going to help with taste as well. And we see this diagram here. That's what my brain was spacing out. So that is on page 497, and it continues on page 498 with a little trick to remember where message is being sent. And you see the little hand that sits on, actually, which way are we going? We're going like that. So temporal, zygomatic, buccal, mandibular, and cervical branches in that facial nerve. The vestibulocochlear, cranial nerve 8. What's that doing for me? That's a big word. Let's break it down. Vestibulocochlear. Because it's got 2 jobs. Correct. Hearing and equilibrium. When we discuss the when we discuss this, discuss the special senses, we're going to see there's two areas. When we come into the inner ear, we're going to come in at an area called the vestibule. And this is where we're going to find receptors, or the beginning of receptors for equilibrium, vestibulo. And then we're going to branch off to another little region called the cochlea. And this is where we're going to find receptors for hearing. So this guy has two branches, vestibulocochlear, cranial nerve 8, hearing and equilibrium. And we see the cochlea there, and then those little, what we call semicircular canals, that's the entrance there, the vestibule. So when we talk hearing and special senses, we'll talk about the two branches of that particular cranial nerve. The glossopharyngeal. We're going to get some back taste from that. Impulses from the pharynx, posterior tongue, pressure receptors. If I stick my finger down your throat, what are you going to do? You're going to gag. Who's going to help me? Glossopharyngeal. Cranial nerve what? IX. It's also going to help when I feel pressure in the back of my throat to fire off certain muscles that are going to then help me swallow things. Back of the throat, we're going to discuss when we discuss the digestive system and the respiratory system. It's called the pharynx. And the digestive and the respiratory system share that pathway right at the top, in the beginning. Part of it is behind your nose. It's called the nasopharynx. Part of it's behind your mouth. It's called the oropharynx. And then part of it's behind your larynx. It's called the laryngopharynx. So the glossopharyngeal cranial nerve 9 is going to help me with information up there. Vegas. And Vegas. Has anybody ever gone to Vegas?
Long time.
You kind of long trip, leaves, and then you know, what stays in Vegas, you know, what happens in Vegas stays in Vegas, yeah. Well, this is how I remember the vagus nerve, cranial nerve 10, because it's kind of the guy that wanders away from all the other nerves that tend to be up in the head region. So the vagus nerve, cranial nerve 10, actually carries impulse from not here, but where? Yeah. So we see some of the different information that's being sent. Vagus is from thoracic, abdominal viscera, baroreceptors, pressure receptors, chemoreceptors, taste buds, posterior tongue, and pharynx. So vagus nerve is a busy little nerve, and we see all the different branches there on page, whatever the heck page that is, 499 in the textbook. Then we have the accessory nerves. Cranial nerve what? 11. So we're learning our Roman numerals here as well. Spinal accessory nerve was its previous name, but when we talk about some of the different muscles exiting skull, be it jugular foramen, trapezius, sternocleidomastoid, we're talking about stuff that happens here. In what region? The neck. When I shrug like this, those muscles that are contracting here. Again, in the head region. And we see that here for the accessory nerves, cranial nerve 11. Then, last but not least, the hypoglossal nerve, cranial nerve 12. That's going to help me with the whole swallowing piece as well. So know your cranial nerves. Some of them are mixed, some of them are sensory, some of them are just motor. Okay? So, we still have a lot to go. So, we are going to finish this chapter when? Tuesday. Hopefully we will start, yeah, so we're gonna end up in that following week, I think. Hopefully we will start chapter 13. So we are going to have a test on this psychotic nervous system coming up soon. It's either going to be next Thursday, I'm giving you a heads up now, or most likely it's going to be the following Tuesday, okay? So, what are you going to do? Yes, thank you.